So let me remind you who I am to preface what I'm going to say. So I'm a computer scientist. I'm interested in this meeting for several reasons. One is I always learn a fascinating amount about neuroscience, which is just mind-blowing to me. So that's a personal pleasure. But my principal professional interest in being here is to try and understand what neuroscience and study of the brain can teach us about ways to think about computing, so that we can design future computer systems, both software and hardware, in a way to solve problems that otherwise we couldn't solve. So that's the bias that I have. So I was as you may recall, those of you who have been here from the bitter beginning, I was in the opening panel. And here's an element that I included in my opening remarks. So I said that these were things that we needed, and I think that the themes in the innermost bullet here align very nicely with the themes we've been hearing over the last 8 talks: the spiking, asynchrony, co-local memory and computing, and approximate computing. So those are all themes that I called out in my early presentation. But the bold major bullet became a point of, to me, what was a fascinating conversation on the first day. And the question, as I've consolidated here, is in trying to understand neural systems or learning or lessons from biology, what is truly intrinsic? That is, what are the essential elements, the core abstractions that we could potentially learn from biology for lessons for computing, and what are instead just evolutionary byproducts. So neural systems, of course, were honed by evolution, working in a highly constrained physio-biochemical space. And so that led to instantiations of solutions, some elements of which are the right abstractions and some of which are just accidental. So I would conjecture that few of the things that biology has honed are pivotal to computational power, and many are artifacts. And it's unclear to me, and it was certainly unclear, I think, collectively to this room, based upon that conversation on Monday, which of those features are truly central core, the right set of abstractions, and which are artifacts. Is spiking one of those? Is the degree of connectivity, heterogeneity in the neural space, commingled computing and memory? It's unclear to me. I think some of these are again optimizations. Some are inherent byproducts of the way evolution has unfolded. But in here, I certainly hope, are somewhere some core computational abstractions and invariants that we need to learn from. I hope we can make progress on this question. Closely related is, so I think I have 4 slides of lessons. Closely related to that is this question of what theoretical models can we abstract from biological systems? And this was, again, a big part of the conversation yesterday. The language yesterday was around the counterpart. What is the counterpart of a Turing machine for neural computation? And actually the difficulty of that gives me even greater appreciation for the work that individuals like Turing did in taking a very messy reality and trying to distill from that something that's essential and simple and actually possible to reason about. That's the key thing. So the counterpart for a Turing machine for neural-inspired computing or for neural computing was discussed yesterday. It would clearly clarify what are the essential strengths of the model. It would enable, and this is hugely important, more formal and disciplined ways of thinking, particularly about algorithms and about computational complexity. It would obviously support hardware design, programming methodologies. It would be incredibly valuable to have that. But there was conversation that helped me see that this might not even be possible. So the essence of this is the concept of a reductionist approach, that if we can figure out what the core concept is, then we can build out of it. But it's certainly plausible that the power of neural systems is not really an element of a reductionist approach, but really it's instead an emergent property of a complex stochastical dynamical system. And maybe it's an emergent property of really any stochastic complex dynamical systems. So perhaps it's a fool's errand to try and identify this core reductionist perspective. I certainly hope not, but as a theoretical computer scientist, it would obviously be very, very attractive to me to have something that I can really sink my teeth into. But I acknowledge that maybe that isn't possible. I will point out that a transistor is a complex stochastic dynamical system. But what we've done is taken that complexity and constrained it and tied it down and built upon it in a way that makes it look like a deterministic digital system or digital entity that we can then build logical systems out of. So we've taken all this inherent complexity and actually constrained it in such a way that we can actually think about and analyze it as a purely digital device, which then allows us to do all kinds of much simpler thinking about the way that we use things. So maybe that even though brains are complex, if we or the underlying biochemistry of brains is very complex, maybe we can still find some intermediate representation that allows us to think about them in a way that hides a vast amount of that complexity. But it's clearly still, as a community, we're still inching our way towards that understanding. Okay, second lesson, spiking is really important, or maybe it's not. So the language that I hadn't heard before, but I think is very well known to the neuroscience community, is that spiking provides a sparse coding in time. And that resonates for me. It's clearly a very useful mechanism for energy efficiency, that spiking is a very energy efficient way to communicate. I'm curious, and maybe the answer is known in this room or known in the community, is there a mathematical relationship between the sparse coding in time concept and the related concept of compressive sensing? Does anyone know? Raise your hand if you know. It's compressive sensing has been this very powerful technique developed over the last few years for information representation in other settings that's efficient beyond the Nyquist limit, and so maybe there's a connection here. I think that's worth exploring if it's not already known. So we heard about several models that people have analyzed or physically built, some of which use spiking, some of which don't. They all seem to work. So maybe spiking is an artifact of evolution. Maybe it's an energy efficiency. I don't know. It's the observation was made that spiking is a great way to quickly get information from a sensor to an actuator. And so you can certainly imagine it being a very primitive element of the way that sensory motor systems would have evolved, and then based upon that entity that was optimized for that, we then built cognition on top of them. But maybe it's essential and maybe it's not. I'm still unclear on that. All right, certainly brains, this is clear, brains suggest all kinds of ideas for computing in an energy efficient way. So we heard several talks about low precision of different sorts that were very intriguing to me, and all the way down to analog systems that were incredibly energy efficient. So as I think about the way we use computers and we build von Neumann's machines and the applications, certainly that my community uses them for, typically they're floating point. In my community, scientific computing, we typically use floating point a lot, and high precision is very important for some of the applications we use them for. But deep understanding of Navier-Stokes equations is not really something the brain has been designed for, not something we really ask the brain to do. So in many ways, computers are disproportionately used for tasks that require high precision. And that may skew the way we think about computing. However, the von Neumann model and the way it does address translation, address translation is not really very error tolerant. And so I think there are inherent aspects of the von Neumann model that require high precision and are noise sensitive. But certainly in some cases, and we heard a great talk this morning, just reducing the floating point precision can be a huge power saving, even keeping the rest of the model intact. And with the talk from yesterday on analog models, we clearly don't always need a von Neumann model. Slow clocks are, of course, okay if you don't want to computers fast, and they're a big win for energy efficiency. We've heard about analog hardware. Spiking communication is an energy efficient alternative. And then, of course, this recurring theme about getting the memory much closer to the processor. And of course, that's a driving design principle in the way that we've constructed memory hierarchies for traditional computers. There's been interest for a long time in moving processing directly into the memories, and Micron is doing some interesting work there that might allow us to do some things. But this deep commingling of memory and processing, to the extent that you can't really even tell what's what in a brain, is well beyond anything that we're thinking about in computer architecture, and potentially something that we can build upon. And then we heard from three different communities, at least here. We heard about experimentalists, neuroscientists who are actually studying the brain. We heard about mathematicians and theoreticians who are thinking about complexity theory and neural models. Then we also heard about what I'll call computational engineers, those that are building systems that allow us now to explore questions that we really couldn't explore before. So I think of these in a holistic ecosystem as follows: that experimental neuroscience continues to discover features and capabilities of brains in ways that to me are really interesting and just really cool, let's be honest. And then we have theoreticians who are trying to synthesize and understand and make sense of these observations. We heard a great talk this morning about some of that work and the encoding principles involved. And now the new element to the science is these large systems that are trying to instantiate, some simplified models of how brains work to, in some cases, solve problems for business, and create businesses. In other cases, just to drive our neuro understanding. So I think that those drive progress in the community in a variety of ways. I think that, for one, they force, we have finite, we're engineering in a finite space, we're making trade-offs. And it forces us to make some hard decisions about what to leave in a model and what to leave out. So it forces a reckoning of some of our more abstract models. And also, as we use these machines, we're going to discover what they actually do, what they can do, and what they can't do in a way that we really can't understand with just paper and pencil models. And so to me, the counterpart here in my world is the emergence of computational modeling and simulation as a different way to do basic physical science. So we've had theory and experiment for a long time, and now we actually have something where we can actually try out models in domains where theory is just too hard or experimentation is just impossible. And we now have that additional leg in neuroscience. And based upon my experience in my own world, I think that will quickly grow to become a very important part of how the community gains understanding. So I think that's really exciting. And these obviously feed on each other in all kinds of ways with great feedback loops in ways that will be really important. So that's what I've got. I want to invite the speakers from this morning's session to come up and participate in a panel discussion about these kinds of topics.